Yeah, like he said, I felt the same way because the way that we learn things is counterintuitive to how light works in reality.
What's up, everybody? Today on Universal Theory, we're going to be talking about energy and special relativity, and that includes time dilation and length contraction. We talked about it with the science guy, so if you haven't seen those shorts, go check them out. A quick shout out, though, to everybody in the comments section. Mr. Meepo, Katya Kaleidoscope, Donnie Holman, Jay Smoke, just everybody. If I missed you, I'm sorry. Let me know in the comments that I missed you, and I'll shout you out next time. We really appreciate it, and because we really appreciate it, here in the next couple of months, once we get to monetization, we're going to start doing comment giveaways. So if you're already down there, you're already going to get used to it, and then you're going to be more likely to win in these giveaways. And we know it's not about winning, it's about helping each other out, but we're going to do it anyways because we want to show you how much we appreciate you. So be looking forward to that in the future. And obviously, everybody who's hitting that like button, if this content is helping you and you think it could help someone else, just share it. It takes a second to share it, and it could reach somebody who needs to hear this information. So please, for me, for you, for them, for the sake of humanity, share our content. How can I spin it to make it important? But no, yeah, so what we do here, we're left brain, right brain, as our symbol shows. As we've talked about many times, I'm going to be approaching things from a scientific perspective. Jordan usually hits the principles, and then we both do a little bit of both because that's how we are trying to learn. Let's talk about energy and special relativity. It's a crazy, counterintuitive thing. I joked about when I first came across this in undergrad, my sophomore year. I was like, nope, my brain is not computing what you're saying. I thought length contraction was an illusion. Like, oh, of course it looks shorter because you're moving fast. Like when I'm moving fast, and it's like, no, it is shorter. And it's like, oh, of course time seems like it's going by slower because you're moving fast. It's like, no, it is going by slower. And then I didn't understand the pictures of the boxes and the light flashing. And there's quite a bit of material about how we came to understand this length contraction and time dilation. But as we talked about in a previous video, energy has to be conserved, and with special relativity, now on top of that, we're equating energy to mass, which we never have really done, even though they have the same units. So we've done it in a classical sense, but in a classical sense, we never cared about the mass. It was a static mass. There was no throw a soccer ball at somebody and it's going to create these nuclear fissions happening where the atoms split up and it's going to release a bunch of nuclear bombs when you throw the soccer ball at somebody, right? We didn't care. We didn't need to care. It was a static mass, and all we cared about was how much it weighed, because then we knew how much momentum it would have when it hit a wall or hit a person or hit the nanny or something. Who knows what it's hitting? And once we started thinking about Einstein came along, and before Einstein, Planck, and there were these individuals before Einstein that were Wolfgang Pauli, who were starting to deal with subatomic because the technology was coming. And we had to start thinking about things differently. It was just what we had to start doing. We had to start subscribing to this new thought process that was the energy is equal to the mass times the speed of light squared plus any momentum it might have times the speed of light. And then that whole thing gets squared. If you wanted to look at the actual equation, you could go check it out. But it's more than just E equals mc squared, because that is the term that matters when it's at rest. And then when it's moving, obviously, we have to account for the motion. But now we're saying, okay, the mass is something that we care about deeply. We care about it deeply. And even stranger, when dealing with light, its energy is equal to Planck's constant times its frequency. So it has nothing, because, right, it's a massless particle. So now it has nothing to do with mass, and well, it's light, so the speed of light, it'd be kind of weird to multiply light by the speed of light. That seems kind of like circular logic. Now we're considering all these other parameters in science, and this was a huge breakthrough for science as a whole, because now we had quite a few new things to look into, and why it's very counterintuitive, like I said at the beginning, is because light is a constant. So I know I've said this before, but let me say it again. When you're moving, light always moves past you at the speed of light. Not because it's so fast, it's like, oh, well, it's 99.9999999% moving past you if you're moving, 50 miles an hour. No. You could be moving at 90% the speed of light, and light would pass you at the speed of light, which is kind of hard to even wrap your head around, because you would think it would just pass you at 10% the speed of light. Because when you're in a car going 10 miles an hour, classically, and a car is going 20 miles an hour, right? It passes you at a speed of 10 miles per hour. It's going 10 miles per hour faster than you. Now substitute you in and light, and no matter how fast you're going, light passes you at the speed of light. And that is something that is hard to wrap your brain around. But when you do, and I know you are having some issues with this, when you do, you understand why with special relativity, time has to dilate, because light has to travel further in the same amount of time. So it's like, length is going to contract to me, time is going to dilate. I don't really, it has to, because I am a constant. With general relativity, which we've talked about, I'll just touch on real quick, right? Space-time gets warped due to energy, and now it has light travels the shortest path time. So the time, it's going to go along the shortest path, not length, but in time. And when space-time gets warped, that shortest path is now longer. It just is. But light still needs to cover that same distance in the same amount of time. So time dilates and lengths contract. And that's the blight of many undergraduate students in physics at this very moment.
Yeah, you got a bunch of people like burning their books and rioting, throwing their degrees away. So they're like, I can't do it.
Yeah, I'm going
home. Like he said, I felt the same way, because the way that we learn things is counterintuitive to how light works in reality. But when I was thinking about it, I'm like, okay, well, I use the principles, I apply them to everything. So when I was thinking about, the basics of how it works, it's like, okay, I know that, for every cause, there's an equal and opposite effect, and everything corresponds. The effect corresponds to the cause to the effect. So the warping of space-time, we know that time slows down. So I'm like, well, that cause and effect. The more massive the object, and of course, there's other variables that you have to take into account, but in general, the more massive the object, the more warped space-time is, and the slower the time will be. So cause and effect. So you can just look out into space, and if you see massive objects, you're like, oh, okay, time slows down.
Yeah.
Gravity's more massive, time slows down, space-time is more warped because of how massive the object is. So cause and effect, it corresponds. So you can, if you have a telescope or you're watching NASA or PBS or something and they're showing you space, or you look at a GIF, or anytime you see it again, just think of cause and effect and correspondence and say, hey, see how massive the object is compared to the other object? Okay, time is most likely slower there because space-time is more warped. So now you'll sound a lot smarter to somebody else who doesn't know.
Yeah, you start applying the principles, and from what we're talking about, and you will sound. Someone will be like, "What? When did you take some online courses, or what's going on?" Like, nah, I just mess with universal theory, bro. Like, that's all.
So just apply the principles. It'll be a lot more simple. Eventually, pretty much with anything, the more that you go over something, eventually it clicks.
Yeah.
But I just thought that was kind of like an anchor for me to conceptualize it, was to just put it into perspective that way.
Yeah.
Same way with light. I'm like, okay, the faster you travel, the slower time will be. So for light, it's like time stands still.
Yeah, exactly.
because it's a constant, and it's the fastest thing that we know of in the universe, because it's massless and it doesn't operate through the Higgs field. So
exactly.
Yeah, so when I think about it, I think cause and effect. Once again, if someone's traveling, like if you're watching Star Trek or you're watching Stargate or anything that has to do with that speed, out in space, or even like if you're running and someone else is running, their perception of time is going to be different. If someone's on a train or someone's in a car or someone's at a spacecraft or you're riding on a beam of light, the faster you travel, the slower time will be. So cause and effect, correspondence. The effect is the cause is you're traveling faster. The effect is time will slow down. So The only thing you can't do is travel at the speed of light.
Yeah. Once you do that, your energy will be conserved. It will be conserved into photons. But
yeah, and you won't exist anymore. Cause and effect.
Yeah, exactly.